The use of the addition method to find the center of area. Article 10.6 of the book Mechanical Systems, Calculations of the Marine Facilities. This is of the professional demand to have the skills to find the centers of the complex geometric figures and the areas of the complex geometric figures. In particular, we need to do that when we decide the issues in the mechanics, dynamics of the rigid body motion, or if we do the calculations or any other analysis of the mechanics of the elastic body as deformations of the elastic body, stretching, compression, sustainability, bending, etc. So the skills are the demand to find the areas of the complex geometric figures and the centers of the location of the centers of the area of the geometric figures. And we have the exercise. Sorry. Exercise is to find the area and the center of the geometric figure shown on the figure 10.6.1a. This is a figure and the elements of the figure, geometric elements. Figure consists of, it could be just a transverse section of any rod, for example, or beam probably. Or it can be just a mechanical, detailed mechanical part, and we of the next subject to find it elements of the motion. But first of all, we must to find the center of the area and the area of this figure. What element of this figure? Figure consists of five main elements. So the first one is the rectangle here, rectangle. The size is A1 and B1, A1, B1, A1 is 80 centimeter, and B1 is 40 centimeter. The length, the width, and next is A2, this triangle. Triangle as well, legs, A1, B1, A2, B2, so A2 45, B2 30. Next, so we have definite one segment to this rectangle. Segment, circular segment of the radius. The center of the radius is at the same point as we have A2 on the axis of the symmetry of this longitudinal symmetry of the this rectangle. The radius of this segment is equal to R3. R3 is 40 centimeter. And the A is the point of location of the center of this curvature, of the center of the curvature, because this is a segment of the circular figure. So A3 we have as well. Next we have A4, the circular cutout, in the detail, the radius of cutout R4, 10 centimeter, and the location A4. We have here. We have as well the B4. B4 is the axis of the symmetry. B is B4. We have 20, and the width of this big rectangle is 40. So this is the axis of symmetry, the same axis in which we have the center of the curvature of this one segment, number 3. And we have as well the neckline, this semicircular neckline with a radius 5, R5 or 10 centimeters, the same as R4 we have. So we have cutouts. Okay. So next we have to make a choice about the coordinate system. Could be the coordinate system of abscissa and ordinate axis. This is the plane statement. So we have ordinate axis directed downward. For example, here we have to do each as comfortable as we can to reduce the amount of the calculations required to find the area of the center of the area of this figure. Then I can just advise, it depends on the experience of the decision about the coordinate systems. Could be the abscissa axis along this big sized rectangular, and the ordinate axis along the one side of the rectangular, and this triangular. Let's consider the formulas we will use to find this. A formula to find the area of this the complex figure. Total of all areas, but we have to remember that the areas of the cutout part, this neckline, this cutout part, we will use with a minus sign as this formula. This is a formula of an abscissa and ordinata of centers of the area, center of the area of the complex figure in the numerator we have total as well. We have a total here of 5 elements. Total of the products of the abscissa, so the center of the area of each part by the area of the each part. It could be negative magnitudes of the areas as well, the cutouts and for the necklines. Okay, so this is okay. Let's begin. Coordinates of center and area of the rectangle one, they are determined. So we have the very simple, and the abscissa is h divided by 2, because h is the length of the rectangle equal to 40, and the area is 80 by 40 width, and length is 3,200 centimeters squared. Coordinates and central area of triangle 2 is the same, not very difficult abscissa, is because for the triangle we have abscissa located 1/3 part from this one leg to the right, and the 1/3 part from this another one leg to the downward, because we have the direction of the y-axis downward. So we will have the half of the width of rectangular plus 1/3 part of this leg, and this will be the ordinate of C2, and the abscissa will be equal to x2. So the rectangular area, we can have just a half of the product of two legs, and 675 centimeters squared. And coordinates of center of the area of triangle 2 is x2 is a. The horizontal leg divided by 3, 45 divided by 3 equal to 15 centimeter, and another one leg is just the half of the width of the big rectangular plus just 1/3 part of the second one leg of this triangle. This is 30 centimeters. So coordinates center of the area and the area of the circular segment 3. Segment 3 is not the most complex segment here, but anyway, we can find this segment area as the area of this definite one sector. We have assigned angle of the angle of we can find ourselves, as because we have right angle triangle and we have one leg is equal the half of the width of this rectangle, half of rectangle B1 width, the 20 centimeter one leg is here in the A3, another one leg A3 assigned 34.64 centimeters. So we can find the alpha is argument of the tangent of this one leg 20 divided by 34.64. This will we have angle of the alpha. We can find the area of this one total sector of this circular sector, but not of the 2 pi angle. 2 pi is the total circle area will be. But if the angle is just limited by 2 angles of alpha, we'll have just a segment. And when if we subtract of the area of this sector of the circle, we'll subtract the area of this right angle triangle twice, because we have another one symmetric here. So we'll have the rest part of the area. This will be the area indicated by the center of C3. Okay, so A3 we found as we have R3 assigned here. We have assigned as A3 the same as R3. R3 is enough because it's this hypotenuse of right angle triangle. So we can find the OO3 size. OO3, what is the OO3 size? OO3 size is the length of this as the O3 is B1. Yeah, the length of this rectangle minus I3. This will be the leg of this R3 right angle triangle. This is a rectangle. We have size of the rectangle and the leg of triangle. So we will have O3 as 45.36 centimeter, and sine alpha we can find as well as just half of the width of the big sized rectangle. That is half of the width. This is width total, but the half of the width is just the leg of the right angle triangle, and we can do that divided by the hypotenuse, because hypotenuse equal to radius. The radius RT is assigned 40. And so we can find that it is 0.5, I mean sine alpha, and alpha will be pi divided by 6 radian. O3C3. So the question is to find the side O3 from the O3 to C3 to have this distance. It is equal to, this is a standard formula how to find the point of the area of the segment of the circle. This is 40/3 multiplied by R3 multiplied by sine alpha. So we consider the sine alpha, and this radius as well. And next we can find that the O3C3 is from the O3, the center assigned by the size R3 from the next one side of the rectangle. So the O3C3 is equal to when we substitute the magnitudes with sine, we don't need the, we need the angle. Pi divided by 6 and sine pi divided 2 of 2 alpha is pi divided by 3. And this, when we substitute the sizes, R is 40, this will be O3C3 equal to 3683. So this is formula from the directory. We can find it ourselves, but it's not out of our interest to do that because a little bit complex. First, we have to find the location of this sector. Next, find of location of the triangle within the sector, within the circular sector, and find the difference. And this is separate issue, but we can use a formula from the directory finding the location of the center of the area of the segment of the circle. Not the sector, but the segment. And next we can find the abscissa of location of the center of the area from the reference point O3 plus O3C3. This is equal to 82.19 centimeter, and the y3 is equal to 0 because we choose y3 is equal to 0. We choose the location of the abscissa axis and the reference point 0 in the place in the centers of a few figures of this cutout of this rectangle and the segment. The centers of the area are on the abscissa axis and with ordinate equal to 0. So we have ordinate equal to 0, y3, and the area. Area we subtract from the area of the sector. We subtract the area of the triangles of two triangles inside the, just only one big triangle. This one big triangle area is equal to the subtractant multiplied by this common factor. So after this, and this is part of the sector area, sector of the circle. So minus and multiplied by the common factor, and then we can find the area of the segment equal 14.48 centimeter. This is the area of this area and the coordinates of the center of the area of this small-sized segment. So small-sized segment of the circle. Segment indicated by the number 3. The coordinates and the area of the circular cutout 4. Circular cutout 4 we have, and the area we understandable because it's a circle, and coordinates x4 and y4 equal to 0 because each is the center of this cutout is on the axis of the symmetry, and the area will be with a minus sign. So this is area with a minus sign because this is cutout. Center and coordinate of the area of the semicircle cutout 5. It is definitely one case. The area is just a half of this one definition because this was the same radius, but a semicircle. But this cutout was a circle, and the abscissa we can find as from the ordinate axis by the horizontal direction to the point of C2 is assigned x5. Is it assigned x5? Exactly. Oh, we can got it. X5, 60 centimeter. Yeah, this have to be assigned x5. Maybe not it here. Yeah, but have to be the x5 is equal to 60 centimeter. And what is the y5? Y5 is half of the width of this rectangle minus the segment from this side of the rectangle to the center of the area of this semicircle. This is from the directory. We have what is as well. It could be the separate issue to find what is location of this center of the semicircle. location from this one, the base segment of the semicircle, diametral base segment. Okay, but we can use the formula from the directory, and y5 equal to b1 divided by 2, b1 divided by 2. b1 is the width of the is half width of this big rectangle. This is a b1. This divided by 2. 2 is because we just only half consider from the abscissa axis of half of the width of this rectangle, and b1 divided by 2, and minus 4 multiplied by r5, the radius of this neck line of the semicircle shape, divided by 3 pi. This is a formula from the directory. We did not consider this as a separate issue, and this is definite one task, and the abscissa, excuse me, ordinata y5 equal to 15.76 centimeter, and the area of this cutout is half of the circle area, p squared divided by 2, and we have minus, because this is cutout, 157.08 centimeter. This is a final table of the areas of the ordinatas and abscissas of these figures and the cutouts. And when we substitute in the formula, we can find the area. The total area of this figure is 3,418.2 centimeters squared, and the coordinates of center of the area with the minuses for the cutouts. Here we have this static moment of the area, because relatively the assigned coordinate system. Because the coordinates of the center of the area equal to the static moment of the this definite one area divided by the area. If you divide the static moment to the area, we will have the coordinate of indefinite one formula, the abscissa of the center of the area of this figure. And this is ordinate, the same formula for the center of the area of the figure, of the total figure having in the numerator the static moment. This is static moment of all the components of the figure, relatively the reference coordinate axis, relatively indefinite one case for the axis of abscissa. So for zeros we have the locations, abscissas of the centers of location, excuse me, ordinates of central location of the cutouts and elements of the figure if they are on the axis abscissa. This will be zeros, and the minuses if this is cutouts and necklines. So this indicated the location of the centers of the area, and that is why, yes, the common center of the area is right here. 3616, 3616, and 520 centimeter with this definite one area. Okay, this was assured to find. Questions and comments. 1061. The approach to find the geometric characteristic of complex figure consisting of regular geometric elements, considering both the material geometric elements and cuts in them and as elements. We use the addition method. Addition method is when we consider the complex figure consisting of the separate geometric parts, which for we can find the area separately and the locations of the centers of the area for each separate elements. Next, we use the formulas when we divide the static moment of. We have to make a choice of the coordinate system, and relatively the chosen coordinate system, we as well define what is the coordinates of the centers of the separate figures of the areas. Okay, then we can use the formulas for the static moments divided by the area. We consider the total figure as by the addition method as the total of the elements, and we do finding the coordinates of the center of the area. 1062, the use of the geometric properties of the material forms and the cuts in them to find the areas. Coordinates of the centers, static moments of the areas relative to the coordinate axis, the total area of the flat figure formed by the geometric shapes, and cuts as well as the coordinates of the center of the area of this figure. Yeah, this is the idea of the addition methods, that we have to decide about the coordinate axis to reduce the number and the amount of the calculations. if we consider the properties of symmetry of separate parts of the mechanical total mechanical figure or geometrical figure. And besides, we subdivide this geometrical figure into the geometric parts, which is simple geometric parts, which is easy, for which is easy to find the area and the location of the center of the area. Thank you.